They're called failed stars, too massive to be planets, yet not massive enough to shine like true stars. These mysterious objects are known as brown dwarfs. What exactly are they, and why do they matter for our understanding of the universe? Stay with us as we uncover their secrets. If you enjoy this journey, please like, subscribe and share, and let us know in the comments what cosmic mystery you'd like us to explore next. Thank you for watching. Now, let's begin. A brown dwarf is defined as an object that is more massive than a planet, but not massive enough to become a star. The word itself signals a category that sits between familiar terms. A star forms when gravity pulls together enough mass for hydrogen fusion to ignite in its core. That steady hydrogen burning is the hallmark of a true star. A planet, in contrast, forms at lower mass, often within the disk around a star, and never comes close to pressures and temperatures that allow any type of fusion in its core. A brown dwarf is positioned between these two. It has too little mass to sustain the long-lasting hydrogen fusion that powers stars, yet often too much mass to be classified comfortably alongside planets. Scientists define the range using mass in relation to the mass of the planet Jupiter. Jupiter is convenient as a scale because it is the largest planet in our solar system and represents a baseline for giant planets in general. Brown dwarfs typically span between about 13 Jupiter masses and about 80 Jupiter masses. At the lower end, an object that has about 13 Jupiter masses can ignite fusion of deuterium, which is a form of hydrogen with an extra neutron for a short time. That process sets a practical lower boundary. At the upper end, around 80 Jupiter masses, the pressures and temperatures in the core finally become sufficient to start stable hydrogen fusion. Above this line, the object is no longer a brown dwarf but a true star. These thresholds are used widely in astronomy, though there is recognition that the boundaries are somewhat blurred by factors such as composition and age. The need for this middle category became clear only in the late 20th century. For much of the history of astronomy, objects were divided into stars and planets, without much thought about what might exist in between. Theory began to suggest that objects with mass below the hydrogen fusion threshold should exist in nature. In the 1960s, astrophysicists calculated that a body of intermediate mass would not reach the conditions needed for sustained hydrogen fusion, but would still collapse under gravity until electron degeneracy pressure, a quantum mechanical effect, provided support against further contraction. The term brown dwarf began to appear in the literature to describe these predicted objects. The name was not chosen to indicate literal colour, but rather to emphasize their place between red dwarfs, which are the smallest and coolest true stars and giant planets, which reflect sunlight rather than producing their own. Brown dwarfs emit their own radiation, but only because they are hot from formation and contraction, not because of a long-lived nuclear fusion. For decades, the idea of brown dwarfs remained purely theoretical. They were predicted to be faint, small and cool, making them difficult to detect with the instruments available at the time. Visible light telescopes were not well suited to finding them, because their peak emission is in the infrared, where their glow can be seen most clearly. Progress came in the 1980s and 1990s with the development of sensitive infrared detectors and all-sky surveys. Discoveries in this period provided the first firm evidence that brown dwarfs exist in large numbers. The initial detections were made in star-forming regions and young clusters where brown dwarfs are hotter and therefore brighter than their older counterparts. Young brown dwarfs can be more easily spotted because they still radiate strongly in the infrared, while older ones fade steadily as they cool. By the late 1990s, astronomers had catalogued dozens, then hundreds of brown dwarfs, confirming them as a genuine class of astronomical object. Defining brown dwarfs required careful work not only in observation, but also in theory. The thresholds of 13 and 80 Jupiter masses are based on nuclear physics. Deuterium fusion is possible above about 13 Jupiter masses because the central temperatures reach several 100,000 degrees. Hydrogen fusion, however, requires a sustained temperature of several million degrees. Only when the mass reaches about 80 Jupiter masses does gravity compress the core enough to achieve this level. Between these values lies the regime of the brown dwarf. Yet even here the edges are not exact. Composition matters an object with higher metallicity, meaning a higher fraction of elements heavier than helium may reach fusion conditions at slightly lower masses. Similarly, helium abundance can alter thresholds. As a result, the boundaries used are approximate, and astronomers accept that some overlap and ambiguity remain in classification. Size is another feature that marks the unusual nature of brown dwarfs. Despite having a wide range in mass, brown dwarfs have sizes comparable to that of Jupiter. This surprising fact arises because increasing mass compresses the object rather than making it much larger. Electron degeneracy pressure resists further compression, leading to a situation where more massive brown dwarfs can even be slightly smaller in radius than less massive ones. This size-mass relationship is an essential aspect of the physics of brown dwarfs and shows why they differ from both stars and planets. Unlike stars which become larger with more mass, brown dwarfs reach a point where adding mass mainly increases density rather than radius. The radiation that brown dwarfs emit is also distinctive. They do not shine with the bright visible light of stars. Instead, their peak emission is in the infrared with spectra that reveal molecular absorption features not seen in hotter stars. These signatures allow astronomers to classify brown dwarfs and to distinguish them from both low-mass stars and giant planets. Early surveys using infrared detectors showed that many faint objects previously overlooked were in fact brown dwarfs. With this recognition, brown dwarfs have come to be seen as an essential piece in the broader picture of how matter organizes in the galaxy, filling the gap between stellar and planetary masses. Brown dwarfs are not rare. Infrared sky surveys have shown that they are scattered widely through the galaxy, found in young clusters near star-forming clouds, and also as isolated objects in the field. They are thought to form by processes similar to star formation, through the collapse and fragmentation of molecular clouds. The distinction is that the collapse halts before reaching the threshold for sustained hydrogen fusion. Thus they represent a continuation of the star formation process down to lower masses rather than a separate category entirely. Their abundance makes them important for understanding the distribution of masses that emerges from cloud collapse, a distribution known as the initial mass function. From definition to discovery, the recognition of brown dwarfs marks a major development in modern astronomy. They are the first objects found to occupy the middle ground between stars and planets, both in theory and in practice. The understanding of their nature rests on clear physical thresholds, observational advances in infrared astronomy, and continued refinements to models of formation and structure. As more are found and studied, the picture grows sharper. What once was only a theoretical gap is now filled with a rich population of faint, cool, and enduring objects that demonstrate the variety of matter in the galaxy. The hydrogen burning limit is a central concept that marks the line between a true star and a brown dwarf. Hydrogen burning means the process of nuclear fusion, in which hydrogen nuclei, also called protons, are pressed together under immense temperature and pressure until they merge into helium. In main sequence stars, which are stars that shine stably for long periods, this reaction provides the energy that balances gravity. Gravity pulls the star inward while the energy released in the core from hydrogen fusion pushes outward. The balance between these two forces gives stars their structure and allows them to remain stable for billions of years. For hydrogen fusion to occur in a sustained way, The core of an object must reach a temperature of at least several million degrees. Only when the pressure is high enough to keep protons close together can the quantum tunneling effect allow them to fuse. This requirement sets a minimum mass for any object that can be called a star. Calculations show that this mass is about 75 to 80 times the mass of Jupiter. Above this threshold, hydrogen fusion begins and continues in a stable manner. Below it, the temperature and pressure do not reach the necessary levels. Objects with masses lower than this limit cannot sustain hydrogen fusion. They may briefly ignite deuterium, which is a heavier isotope of hydrogen, that fuses more easily, but they do not reach the stable, long-lasting hydrogen-burning stage. Instead, they cool gradually over time, radiating away the heat left over from their formation. This is why they are called brown dwarfs rather than stars. The hydrogen-burning limit is therefore both a physical boundary and a practical classification tool. It draws the line between self-sustaining stars and fading substellar objects. The concept is widely accepted, though small uncertainties remain because the exact value depends slightly on the composition of the object. The theoretical reasoning for this limit was worked out in the 20th century as astrophysicists began to model the balance between gravitational compression and nuclear fusion. For a star, the mass determines the central pressure. More mass means stronger gravity and higher central temperatures. For the smallest stars called red dwarfs, the balance is just barely sufficient to sustain fusion at a very low rate. For a brown dwarf, even though gravity still pulls strongly inward, the compression is halted by a different type of pressure, called electron degeneracy pressure. This pressure arises because electrons, the tiny particles surrounding atomic nuclei, cannot be packed into the same energy state. This is a rule of quantum mechanics called the Pauli exclusion principle. When gravity compresses matter to extremely high density, the electrons push back, creating a form of pressure that does not depend on temperature. This degeneracy pressure prevents the core from reaching the temperature needed for hydrogen fusion, even if the mass is close to the threshold. The hydrogen burning limit is therefore not an arbitrary value, but the point at which gravitational compression barely wins over degeneracy pressure. Evidence for this limit is found in observations of the smallest stars. Red dwarfs just above the threshold shine stably and exhibit the expected features of hydrogen fusion. Objects just below the threshold show a very different evolution. They are brightest when young because they are still contracting and radiating heat from formation, but they fade steadily with age, showing no ongoing nuclear source of energy. Astronomers confirm this distinction by examining star clusters where groups of objects of similar age can be compared. The presence of very faint objects below the hydrogen burning limit alongside brighter stars provides a natural laboratory for understanding where the division lies. An important aspect of the hydrogen burning limit is its relationship to the lifetime of stars. Low-mass stars that are just above the limit burn hydrogen very slowly, meaning they can last for trillions of years, far longer than the current age of the universe. In contrast, brown dwarfs below the limit have no such long-term fuel. They simply cool over time, becoming fainter and colder. This contrast shows why the hydrogen burning limit is more than a technical boundary. It determines whether an object will shine for cosmic timescales or fade into obscurity. The limit also influences how astronomers classify objects when they are first discovered. A newly found faint object must be studied carefully to determine if it is a very low-mass star or a brown dwarf. Spectroscopy, which is the measurement of light at different wavelengths, plays a key role. A star above the limit will show features consistent with high-temperature hydrogen fusion in the core. A brown dwarf below the limit will instead display signatures of molecules such as water, methane, or ammonia in its atmosphere which are not seen in stellar spectra. Measuring the luminosity or total energy output also helps. If the energy is too low for sustained fusion at the estimated mass, the object is categorized as a brown dwarf. Theoretical models combined with observational evidence give strong support to the existence of the hydrogen burning limit around 75 to 80 Jupiter masses. Yet astronomers note that the exact dividing line may shift slightly with metallicity. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star or brown dwarf. Higher metallicity increases opacity in the interior, which can affect how heat is transported and therefore shift the fusion threshold. This makes the boundary not a single sharp number, but a range depending on composition. This nuance is important when studying populations of objects in different environments, such as clusters with different chemical histories. The hydrogen burning limit remains a clear dividing marker in astronomy. It sets the stage for understanding why brown dwarfs form as they do, why they evolve differently from stars, and why their spectra carry the signatures of cooling rather than of steady fusion. It is the point where nature separates two pathways, one leading to a stable, long-lived star, and the other leading to a cooling, fading brown dwarf. As observations have expanded with infrared telescopes and wide surveys, this theoretical boundary has been confirmed again and again, making it one of the fundamental features of stellar and substellar astrophysics. The deuterium burning threshold is a second important concept in the study of brown dwarfs. Deuterium is a form of hydrogen that contains not only one proton, but also one neutron in its nucleus. This additional neutron makes it fuse at lower temperatures than ordinary hydrogen. For this reason, objects with lower mass than stars but higher mass than giant planets can briefly ignite deuterium in their cores, even though they cannot sustain regular hydrogen fusion. The threshold for this process occurs at about 13 times the mass of Jupiter. Below this level, even deuterium fusion is not possible, and the object is considered to be a planet. Above it, up to the hydrogen burning limit of about 75 to 80 Jupiter masses, deuterium burning can occur. This distinction is part of the reason why the lower mass limit for brown dwarfs is often set at about 13 Jupiter masses. Deuterium burning is short-lived because deuterium is not abundant in the universe. Most of the deuterium present today was created during the earliest moments after the Big Bang, when the universe was only a few minutes old. In stellar interiors, deuterium is quickly consumed and converted into helium. The abundance of deuterium is only about 1 part in 100,000 relative to hydrogen. This small supply means that even when deuterium burning occurs inside a brown dwarf, it lasts only a short time, typically a few million years at most. Compared to the billions of years during which stars burn hydrogen, this is only a fleeting stage. Once the available deuterium is consumed, the object begins to cool, steadily powered only by the gradual release of gravitational energy and residual heat. The physics of deuterium burning also helps to clarify why brown dwarfs occupy a middle ground between stars and planets. A giant planet such as Jupiter never ignites deuterium fusion because its mass is below the threshold. A more massive object, such as one with 15 or 20 Jupiter masses, will briefly fuse deuterium, making it behave differently in its earliest evolution. The heat generated from this fusion causes the brown dwarf to radiate more strongly in its youth, delaying its cooling compared to a planet. However, once the deuterium is gone, both planets and brown dwarfs follow similar paths of cooling and fading. In this sense, deuterium burning does not provide a long-term energy source, but it does provide an important dividing line. Observations confirm that deuterium burning plays a role in the early lives of brown dwarfs. In young star-forming regions, brown dwarfs with masses above the threshold appear brighter than models without deuterium burning would predict. This excess brightness can be explained by the additional energy released by the short-lived fusion process. As these objects age, the effect fades. and they become indistinguishable in brightness from slightly less massive brown dwarfs that never burned deuterium. This pattern is one way astronomers can test models of substellar evolution. By comparing young populations to older ones, they see the imprint of deuterium burning in the earlier stages. The presence or absence of deuterium burning also influences how astronomers classify borderline objects. A massive exoplanet detected around another star may be estimated to have a mass of 15 Jupiter masses. Some definitions would classify it as a brown dwarf, since it is above the deuterium burning threshold. Others argue that the mode of formation is more important. If the object formed in a circumstellar disk like a planet, it might be called a planet even if it could burn deuterium. If it formed by direct collapse of a gas cloud like a star, it might be called a brown dwarf. This ambiguity shows that the deuterium burning limit is a physical boundary, but not always a simple classification tool. Scientists often acknowledge both the physical and the formation-based definitions depending on context. Deuterium burning also provides a way to test theoretical models of matter at high density. The temperatures reached in brown dwarf interiors are lower than those in stars, but still high enough to allow deuterium reactions. Studying the effects of this process helps constrain equations of state, which describe how matter behaves under extreme pressure and temperature. These models are important not only for brown dwarfs, but also for giant planets and low-mass stars. By comparing observed brightness and spectra of young brown dwarfs to predictions, astrophysicists refine their understanding of the interior physics. The transient nature of deuterium burning underscores the idea that brown dwarfs are not sustained by any long-term nuclear process. Their brief ignition of deuterium is like a passing phase rather than a defining feature. Still, this phase is crucial for setting boundaries. Without it, the line between giant planets and brown dwarfs would be more arbitrary. With it, there is a measurable difference in the internal processes of objects above and below 13 Jupiter masses. Astronomers therefore use the deuterium burning threshold as one of the guiding markers when studying the population of low-mass objects. In summary, the deuterium burning threshold highlights both the similarities and differences between planets and brown dwarfs. It shows that some brown dwarfs can briefly act like stars in their early years, producing energy through nuclear reactions while others do not. It also shows why brown dwarfs cool and fade like planets in the long run rather than shining for billions of years like stars. The threshold provides a natural dividing line in mass, one grounded in nuclear physics and cosmological abundances. While it does not resolve every classification debate, it provides a clear physical process that separates two categories. In the study of brown dwarfs, the deuterium burning limit is therefore a cornerstone linking the physics of the early universe to the lives of faint cooling objects scattered throughout the galaxy. The question of how brown dwarfs form is central to understanding their place in the universe. Stars form by the gravitational collapse of dense regions within molecular clouds. Planets, by contrast, usually form within the rotating disks of gas and dust that surround young stars. Brown dwarfs appear to arise from processes that resemble both of these origins, and astronomers continue to investigate which pathways are most common. Several formation scenarios are proposed, each supported by certain observations but also leaving open questions. The most straightforward scenario is direct collapse, similar to how stars form. A clump of gas in a molecular cloud becomes dense enough that gravity overwhelms internal pressure, causing it to collapse. If the mass of the clump is large, the collapse leads to a star. If the mass is smaller, below the hydrogen burning limit, the collapse still occurs, but the final object is a brown dwarf. This pathway suggests that brown dwarfs are simply the low-mass tail of star formation. Support for this idea comes from the presence of brown dwarfs in young star-forming regions often mixed together with stars of different masses. The spatial distribution of brown dwarfs in these clusters often mirrors that of stars, reinforcing the view that they share a common origin. Another proposed pathway is disk fragmentation. Around young stars, massive disks of gas and dust sometimes become gravitationally unstable. Parts of the disk can clump together and collapse under their own gravity. If a fragment is massive enough, it can form a companion object. Depending on the mass of the fragment, the result could be a giant planet, a brown dwarf, or in some cases even another star. Disk fragmentation explains the existence of brown dwarfs found as companions at wide distances from their host stars, since such distances are difficult to explain with planet-like formation alone. Observations of young disks with spiral structures and clumps provide evidence that such instability occur. A third scenario is the ejection model. In this view, brown dwarfs begin forming like stars within a cluster, but are ejected by gravitational interactions before they can gather enough mass to ignite hydrogen fusion. In crowded star-forming regions, multiple protostars interact strongly. If a forming object is thrown out early, it is cut off from the gas reservoir that would otherwise allow it to grow. The ejection halts its mass build-up, leaving it as a substellar object. Support for this idea comes from the observation that many brown dwarfs are found in isolation, not bound to stars. Their free-floating presence suggests they may have been expelled from their birth environments. Computer simulations of star-forming regions show that such ejections are plausible and may produce a population of low-mass objects consistent with observed numbers. These pathways are not mutually exclusive. It is possible and indeed likely that brown dwarfs form through a combination of processes depending on environment. In dense clusters, ejection may be common. In wide star-forming regions, direct collapse of small clumps may dominate. In disks around stars, fragmentation can add another route. The challenge for astronomers is to determine which mechanisms are most frequent and under what conditions each operates. This requires careful statistical study of brown dwarf populations, their locations, and their relationships to other objects. Evidence also comes from the presence of disks around young brown dwarfs. Observations with infrared telescopes such as Spitzer and the Atacama Large Millimeter Array show that some brown dwarfs retain disks of gas and dust similar to those around young stars. These disks may even form planets of their own. The existence of such disks supports the idea that brown dwarfs share formation pathways with stars rather than being simply massive planets. However, the presence of disks does not rule out ejection, since an ejected object could still retain a small disk. The idea of a formation continuum is increasingly accepted. Instead of strict categories, there may be a range of outcomes determined by initial conditions. The same molecular cloud may produce stars, brown dwarfs, and planets with boundaries set by mass, environment, and dynamics. In this view, brown dwarfs represent a natural extension of the star formation process, rather than a separate class. Still, differences in detail matter, because they influence how many brown dwarfs exist and what roles they play in galactic evolution. An important tool in studying formation scenarios is the initial mass function, which describes how many objects form at each mass in a given star-forming region. Measurements show that the number of objects increases toward lower masses, then flattens or declines around the brown dwarf regime. The shape of this curve carries information about the processes at work. If ejection were dominant, one might expect many more brown dwarfs than are observed. If direct collapse were dominant, the distribution might more smoothly extend from stars downward. Ongoing surveys aim to refine these counts to distinguish between models. The spatial distribution of brown dwarfs also provides clues. If they are often found near massive stars or in crowded regions, ejection may be favoured. If they're found in the same general environments as low-mass stars, direct collapse may be favoured. If they are found widely separated from stars yet still bound in binary systems, disk fragmentation may play a key role. Observations so far reveal examples of all these situations, which strengthens the idea that multiple pathways contribute. The study of formation scenarios is not only about origins, but also about consequences. Brown dwarfs influence their environments during their youth by emitting radiation and driving outflows. Their disks may form planetary systems, though probably smaller ones than those around stars. Their numbers affect the overall mass budget of galaxies, especially at the low mass end. Understanding how they form therefore connects to broader questions about galactic structure and evolution. Despite decades of study, the precise balance between these formation pathways remains unresolved. Astronomers continue to refine simulations to conduct deeper infrared surveys and to analyze the chemical signatures of young brown dwarfs and their disks. Each new dataset helps to narrow the possibilities. The complexity of molecular clouds with turbulence, magnetic fields and variable densities ensures that no single pathway can explain all cases. Brown dwarfs, by sitting at the edge of stellar formation, provide a sensitive probe of these processes. Their existence confirms that star formation does not have a sharp cutoff, but a gradual decline into the substellar regime. In summary, the origin of brown dwarfs likely involves a blend of direct collapse disk fragmentation and ejection, with the balance depending on local conditions. They form not as an anomaly but as a natural outcome of the same physics that produces stars and planets. Their diversity in environments, companions and disks reflects the variety of ways nature assembles matter under gravity. The study of their formation continues to refine our understanding of the delicate thresholds that separate stars from planets and the many pathways that bridge the gap. The interior structure of a brown dwarf is shaped by the balance between gravity pulling inward and pressure pushing outward, and unlike in stars, this balance does not rely on the continuous energy from hydrogen fusion. Instead, a different physical process called electron degeneracy pressure provides much of the support that keeps a brown dwarf stable. To understand this one begins with the fact that a brown dwarf is born hot from the collapse of a gas cloud. As it contracts, the central regions become compressed to very high densities. Normally in a star, this compression raises the temperature until hydrogen nuclei can fuse into helium, releasing energy and halting further collapse. In a brown dwarf, the mass is not sufficient to reach the required core temperature for sustained hydrogen fusion. Instead, as the matter is squeezed tighter, the electrons around the atomic nuclei reach a point where the laws of quantum mechanics intervene. Electrons cannot all occupy the same energy state. This rule, known as the Pauli exclusion principle, prevents them from being forced into identical configurations. When the density becomes high, electrons begin to resist further compression, not through thermal pressure, but through quantum pressure. This resistance is electron degeneracy pressure. It does not depend strongly on temperature, which means that even as a brown dwarf cools, this pressure remains. It halts the collapse and allows the brown dwarf to exist in a stable state even without fusion as a central power source. The structure of a brown dwarf is therefore different from that of a star. In a star, the outward push from fusion energy balances gravity. In a brown dwarf, it is the quantum mechanical properties of electrons that provide the balance. This difference leads to unusual size properties. Brown dwarfs across a wide range of masses are similar in size, comparable to Jupiter. Adding more mass to a brown dwarf does not make it much larger. Instead, more mass compresses the object, making it denser. At the high end of the mass range, close to the hydrogen burning limit, a brown dwarf may even be slightly smaller in radius than a lighter one because the stronger gravity squeezes it further despite the degeneracy pressure. This inverse relationship between mass and size is a hallmark of degenerate objects and is also seen in white dwarfs, which are remnants of stars supported entirely by electron degeneracy pressure. Inside a brown dwarf, the layers follow a structure similar in concept to stars but with distinct differences. At the surface there is an atmosphere where molecules and sometimes clouds form. Beneath this there are convective layers where hot material rises and cooler material sinks, transporting heat outward. Deeper inside, the density and pressure rise dramatically. In the core, the density can reach values thousands of times higher than water. Temperatures in the core can reach several million degrees, enough for deuterium fusion in more massive brown dwarfs, but not enough for sustained hydrogen fusion. Because the energy flow is not sustained by nuclear reactions, the entire interior gradually cools over time, with heat being transported outward and radiated away. The cooling process shapes the observable properties of brown dwarfs. When young, they are hot and relatively bright in the infrared. Their interiors are still contracting, releasing gravitational energy. Over hundreds of millions of years, the cooling progresses and the interior temperature drops. Without a central fusion source to replenish energy, the brown dwarf becomes fainter and colder. This cooling trajectory is predictable in broad terms, allowing astronomers to estimate the age of a brown dwarf if its brightness and spectrum are known. However, uncertainties remain due to factors such as atmospheric composition and cloud cover, which affect the radiation escaping from the surface. Magnetic fields are another feature linked to the interior structure. Brown dwarfs are fully convective, meaning that the motion of hot material occurs throughout their interiors, unlike stars such as the Sun, which have both radiative and convective zones. Convection combined with rotation can generate magnetic fields through a dynamo process. These magnetic fields are thought to drive radio emissions and even aurora-like phenomena observed in some brown dwarfs. The presence of magnetism in objects without sustained fusion shows that internal motions, not nuclear burning, are sufficient to produce dynamic magnetic environments. The study of brown dwarf interiors is closely tied to equations of state, which describe how matter behaves under extreme conditions of temperature and density. Laboratory experiments cannot reach the same range of pressures and densities found inside brown dwarfs, so astrophysicists rely on theoretical models tested against observations. By measuring mass and radius for brown dwarfs in binary systems, astronomers can compare results to predictions. These measurements confirm that electron degeneracy pressure plays the dominant role in determining size and structure. One of the most striking features of brown dwarf interiors is the smooth transition between planetary and stellar physics. At lower masses, the physics resembles that of giant planets, with molecular hydrogen in the outer layers and metallic hydrogen forming under pressure deeper inside. At higher masses, the physics approaches that of low-mass stars with higher core temperatures and partial nuclear processes. Brown dwarfs therefore serve as laboratories for studying matter in a regime that bridges planetary and stellar interiors. This role makes them particularly important for understanding both the physics of dense matter and the evolution of objects at the boundaries of stellar classification. Cooling models of brown dwarfs must also include the effect of initial conditions. A newly formed brown dwarf retains heat from its collapse, and from any brief deuterium burning if it is above the threshold. This initial energy affects its early brightness. Over time, the memory of these early processes fades as the brown dwarf settles into steady cooling. However, for young brown dwarfs in clusters, the early differences remain significant, influencing their spectra and luminosity. Observations of clusters at different ages provide benchmarks that test these models, helping refine our understanding of how interior structure and cooling interact. In essence, the interior of a brown dwarf is governed not by the ongoing burning of hydrogen, but by the quantum mechanical properties of electrons and the slow release of residual heat. This difference explains why they do not shine like stars yet, also why they do not collapse like ordinary matter under gravity. They occupy a unique state where dense matter is supported by principles that do not depend on temperature, allowing them to persist for billions of years while gradually fading. The study of their interiors connects fundamental physics with astrophysical observation, linking the small-scale rules of quantum mechanics to the large-scale existence of faint objects drifting through the galaxy. A defining feature of brown dwarfs is their gradual cooling over time. Unlike stars, which maintain stable brightness by fusing hydrogen in their cores, brown dwarfs have no long-lasting nuclear energy source. Instead, they begin their lives hot, radiating the leftover heat from gravitational collapse, and then steadily fade as that heat is lost to space. This slow decline shapes every aspect of their evolution, and is one of the main reasons why brown dwarfs appear so faint in observations. When a brown dwarf first forms, it is relatively bright in the infrared. The collapse of the initial gas cloud converts gravitational potential energy into thermal energy, heating the object throughout. If the brown dwarf is massive enough, it may briefly burn deuterium, which delays cooling slightly. But once the deuterium is gone, no new energy is produced in the core. From that moment onward, the brown dwarf follows a steady path of cooling and contraction. The rate of this cooling depends on mass age and atmospheric properties, but the overall trajectory is always downward. In the first tens of millions of years, young brown dwarfs can still reach temperatures of several thousand degrees, similar to very low-mass stars. At this stage, they may be difficult to distinguish from stars based on appearance alone, since both emit strongly in the infrared. As time passes, however, the difference becomes clear. A star of similar mass will maintain its brightness, but the brown dwarf will dim. Over hundreds of millions of years, the brightness declines by large factors, and the spectrum shifts toward longer wavelengths. This shift reflects the drop in surface temperature. Molecules such as water, methane, and ammonia begin to appear in the atmosphere as temperatures fall, leaving distinctive fingerprints in the spectrum. Over billions of years, the cooling continues. A brown dwarf that is several billion years old can have a surface temperature of only a few hundred degrees above absolute zero, not much warmer than a household oven. Some of the coldest brown dwarfs discovered belonging to the I spectral class are so cool that their temperatures are close to those of the human body. At this stage, the objects are extremely faint, radiating almost entirely in the mid-infrared. Detecting such objects requires sensitive telescopes equipped to see at these wavelengths, such as the Wide Field Infrared Survey Explorer and the James Webb Space Telescope. The absence of stable fusion means that the luminosity of a brown dwarf is directly tied to its age. A young brown dwarf is brighter than an old one of the same mass. This makes it difficult to estimate the mass of a brown dwarf from brightness alone. An object that appears faint could either be a low-mass young brown dwarf or a more massive old one that has cooled. To resolve this, astronomers use additional information such as membership in a star cluster, which provides an age or measurements of orbital motion in a binary system which reveal mass directly. These constraints allow models of cooling to be tested and refined. Cooling also explains why brown dwarfs are spread across a wide range of spectral types. At birth, they resemble low-mass stars with warm atmospheres and relatively simple spectra. As they age and cool, their atmospheres change. Clouds form and dissipate, new molecules dominate, and the emission shifts toward longer wavelengths. This progression defines the LT and Y spectral classes, which are assigned based on surface temperature and spectral features. The cooling process therefore connects directly to how astronomers classify and identify brown dwarfs. Theoretical models of cooling rely on solving equations that describe how heat flows from the core to the surface. In brown dwarfs, convection dominates much of the interior, meaning that hot material rises while cooler material sinks, transporting energy outward efficiently. Near the surface, radiation becomes important as photons escape into space. The efficiency of these processes depends on composition, cloud cover, and the presence of molecules that absorb or scatter radiation. This complexity means that cooling curves for brown dwarfs are sensitive to atmospheric physics as well as interior physics. Observations of brightness and spectra across a wide range of ages provide the data needed to test these models. An additional complication arises because cooling is not uniform across all masses. More massive brown dwarfs begin hotter and cool more slowly since they store more internal heat. Less massive ones begin cooler and fade more quickly. This mass dependence leads to overlapping observational properties. For example, a 10 Jupiter mass brown dwarf 100 million years old may appear similar in brightness to a 50 Jupiter mass brown dwarf that is 10 billion years old. Without knowledge of age, distinguishing them is difficult. This degeneracy between mass and age is one of the persistent challenges in brown dwarf astronomy. Despite these challenges, the general trend is clear: all brown dwarfs become cooler, dimmer and redder in color as time passes. Eventually, after many billions of years, they approach temperatures only slightly above the background temperature of the universe itself. In principle, after trillions of years, a brown dwarf would cool to the point where it emits almost no detectable radiation. However, the universe is not old enough for any brown dwarf to have reached that stage. All known brown dwarfs are still radiating detectable heat, though the faintest ones are already colder than most stars ever become during their lives. The gradual cooling of brown dwarfs provides a natural chronometer for studying populations. By observing a group of brown dwarfs and comparing their brightness and spectra, astronomers can infer relative ages. In clusters where the age is independently known, brown dwarfs serve as test cases for cooling models. These comparisons help refine the physics of dense matter convection and molecular atmospheres. In this way, the fading light of brown dwarfs becomes a tool for understanding not only their own evolution, but also the processes that shape low-mass objects in general. Cooling also highlights the contrast between stars and brown dwarfs in terms of cosmic significance. Stars maintain a stable energy output for billions of years, providing the light and heat that make planets habitable. Brown dwarfs, by contrast, offer no such stability. Their light fades too quickly, and their environments grow steadily colder. Yet their very existence demonstrates the range of outcomes in star-forming regions, showing that not all collapsing clouds succeed in igniting hydrogen fusion. Some stop short, becoming long-lived but fading relics of the process. In summary, the cooling of brown dwarfs is their defining evolutionary path. They begin hot and bright, lose energy without replacement, and fade into colder, dimmer states as the billions of years pass. This trajectory explains why they are faint, why their spectra change with time, and why they are challenging to detect. Cooling is not simply a side effect of their nature. It is their destiny, the physical process that governs every stage of their observable lives. The atmospheres of brown dwarfs are complex layers where chemistry, condensation, and dynamic processes shape what we see in their spectra. Because brown dwarfs lack steady hydrogen fusion, their surfaces cool over time, and as they cool, the types of molecules and condensates that can form in their atmospheres change. These changes create clouds of exotic materials, shifting chemical balances and weather patterns that can vary over hours or days. The study of these atmospheres provides much of the information astronomers use to classify brown dwarfs and to understand their cooling histories. At the highest temperatures, newly formed brown dwarfs resemble very cool stars. Their atmospheres are dominated by atomic species such as sodium, potassium, and metal oxides like titanium oxide and vanadium oxide. As the brown dwarf cools below about 2000 degrees, these compounds begin to condense out of the atmosphere. Elements such as silicon and iron combine into solid grains, forming cloud particles that float in the upper layers. These clouds are not like the water clouds on Earth, but rather clouds of silicates and iron droplets. They scatter and absorb infrared radiation, altering the spectrum and reducing the brightness at certain wavelengths. As cooling continues, these silicate and iron clouds become thicker, and the atmosphere enters what astronomers classify as the L-spectral type. The spectra of L-dwarfs show strong signatures of metal hydrides and alkali metals, along with evidence of dust and clouds. These features make the light of L-dwarfs distinctly red in the near-infrared. The cloud layers may also be patchy, leading to brightness variations as the brown dwarf rotates. This patchiness provides a clue that weather patterns perhaps similar to storms and belts seen on giant planets are present in brown dwarf atmospheres. When temperatures fall, further approaching about 1200 degrees, methane becomes stable in the atmosphere. The appearance of methane absorption bands marks the transition to the T-spectral class. At this stage, many of the silicate and iron clouds settle below the visible atmosphere, leaving a clearer view into the layers below. The spectra of T-dwarfs show deep methane absorption features, especially in the near-infrared, along with water vapor bands. The overall color shifts to bluer tones in the infrared compared to L-dwarfs. The transition from dusty cloudy L-dwarfs to clearer methane-rich T-dwarfs is a dramatic one, and many studies focus on understanding how cloud dynamics produce the observed changes. Still cooler are the Y dwarfs discovered only in the past decade with sensitive infrared surveys. In these objects, surface temperatures are below about 500 degrees. At such low temperatures, ammonia becomes a prominent absorber, and new condensates such as sulfide and water clouds may form. The spectra of Y dwarfs are difficult to obtain because they are so faint, but early results confirm that their atmospheres are among the coldest ever observed outside the solar system. Some Y dwarfs may have surface temperatures similar to Earth's ambient environment, yet they still radiate faint infrared light from their residual heat. The chemistry of brown dwarf atmospheres is governed by equilibrium processes, but is also influenced by vertical mixing. Hotter gases from deeper layers can be transported upward, bringing molecules such as carbon monoxide into regions where methane would otherwise dominate. This disequilibrium chemistry alters the expected balance and creates features that differ from simple predictions. Observations show that such mixing is common, indicating that brown dwarf atmospheres are not static but dynamic, with constant circulation and exchange between layers. Cloud formation is another area of active research. The sizes, compositions, and distributions of cloud particles affect how radiation escapes. Some models treat the clouds as uniform layers, while others allow for patchy coverage and variable thickness. Variability studies, where astronomers monitor brown dwarfs over hours and days, reveal periodic changes in brightness consistent with rotating cloud structures. These variations demonstrate that weather on brown dwarfs can be as dynamic as on giant planets, though involving different materials and occurring at much higher pressures and temperatures. The presence of clouds also influences how brown dwarfs cool. Thick cloud layers trap heat, slowing the escape of radiation, while clearer atmospheres allow more rapid cooling. This feedback means that atmospheric physics must be included in models of brown dwarf evolution. Without accounting for clouds, predictions of luminosity and color at given ages would be inaccurate. Observations from telescopes such as the Hubble Space Telescope, the Spitzer Space Telescope, and now the James Webb Space Telescope provide crucial data to test these models, capturing spectra across a wide range of wavelengths where different molecules and cloud effects are visible. Comparisons between brown dwarfs and giant planets are especially useful in studying atmospheres. Many exoplanets discovered by direct imaging show similar features to brown dwarfs, including clouds of silicates and methane absorption. Because brown dwarfs can be studied without the glare of a host star, they serve as natural laboratories for understanding planetary atmospheres under conditions that cannot be recreated on Earth. The lessons learned from brown dwarfs feed directly into models of exoplanets, especially hot Jupiters and young giant planets. The variety of atmospheric phenomena in brown dwarfs also highlights the continuum between stars and planets. At high temperatures, the atmospheres resemble those of very low-mass stars with atomic lines and hot molecular bands. At intermediate temperatures, clouds of silicates and iron dominate, creating red spectra and variability. At lower temperatures, methane and ammonia define the spectrum, resembling giant planets more than stars. Finally, at the coolest end, water clouds and exotic condensates may form, bridging the gap between the coldest brown dwarfs and gas giant planets. This continuous progression illustrates how the cooling of a brown dwarf drives atmospheric evolution step by step. Despite major advances, uncertainties remain in modeling brown dwarf atmospheres. The details of cloud particle formation, the role of vertical mixing, and the influence of metallicity are all active areas of research. Metallicities affect the balance of molecules, with higher metal content producing stronger absorption bands and altering cloud composition. Variability studies also continue to reveal surprises such as brown dwarfs, with irregular brightness changes that suggest rapidly evolving weather systems. These complexities remind astronomers that even without the energy of fusion, brown dwarfs are dynamic, ever-changing objects. In summary, the atmospheres of brown dwarfs are layered, cloudy, and chemically diverse. They begin with atomic and molecular features similar to stars, develop clouds of silicates, and metals shift to methane-dominated spectra, and finally reach ammonia and water, rich states at the coldest end. Clouds' chemistry and circulation combine to shape the spectra and brightness we observe. By studying these features, astronomers gain insight into the processes that govern not only brown dwarfs, but also the atmospheres of giant planets beyond the solar system. The atmosphere is the gateway through which a brown dwarf reveals itself, making its study central to the science of these faint and enigmatic objects. The classification of brown dwarfs into spectral classes L, T, and Y provides a framework for understanding how their observable properties change as they cool. Unlike the familiar sequence of stellar types that extends from hot O and B stars to cooler M dwarfs, the brown dwarf classes represent temperatures far below the stellar domain. They are defined not by hydrogen fusion, but by atmospheric molecules and condensates that become stable at low temperatures. This classification is central to studying the life histories of brown dwarfs because it links temperature, chemistry, and brightness in a systematic way. The L class includes brown dwarfs with surface temperatures ranging roughly from 2000 degrees to about 1200 degrees. At these temperatures, the atmospheres are warm enough that molecules like water vapor, carbon monoxide, and metal hydrides appear prominently. Silicate and iron clouds also form, giving L dwarfs a dusty and red appearance in the infrared. The spectra of L dwarfs are marked by strong absorption lines of alkali metals such as sodium and potassium. These lines become broadened by the high pressure of the atmosphere, creating distinctive features that identify the class. The presence of thick cloud layers contributes to their red colors and to variability, since patchy clouds can produce fluctuations as the dwarf rotates. L dwarfs are therefore often studied for evidence of dynamic weather patterns, in addition to their chemical composition. As cooling proceeds, methane begins to dominate the chemistry. This marks the transition to the T class, with temperatures from about 1200 degrees down to about 500 degrees. Methane is stable only at lower temperatures, so its appearance is a defining feature of T-dwarfs. Their spectra show deep methane absorption bands in the near-infrared along with water vapor. The silicate and iron clouds that dominated in L-dwarfs tend to sink below the visible atmosphere in T-dwarfs, leaving clearer skies. This clarity allows astronomers to probe deeper layers and measure molecular abundances more precisely. T-dwarfs are typically bluer in the infrared than L-dwarfs because cloud opacity is reduced. The transition from L to T has been challenging to model, since it involves not only cooling, but also the settling and breaking up of cloud layers. Observations of variability during this transition suggest that clouds may dissipate unevenly, creating dramatic changes in brightness and colour over relatively small temperature ranges. At the coolest end of the known sequence are the wide dwarfs, with temperatures below about 500 degrees, some as low as 250 degrees. These objects represent the coldest substellar atmospheres yet observed. The discovery of wide dwarfs was made possible by space-based infrared telescopes, such as the Wide Field Infrared Survey Explorer, which could detect their faint emissions at long wavelengths. The spectra of wide dwarfs are difficult to obtain because they are extremely faint, but available data show strong signatures of water and ammonia, as well as evidence for new types of condensates, such as sulfides and water ice clouds. Wide dwarfs are remarkable for having temperatures comparable to those on Earth's surface, yet they remain self-luminous due to residual heat from formation. Their faint glow provides direct evidence of how brown dwarfs evolve toward invisibility as they age. The classification into LT and wide dwarfs is not only descriptive, but also provides tools for measuring fundamental properties. By comparing spectra to models, astronomers can estimate effective temperatures, surface gravities, and compositions. These estimates help constrain ages and masses when combined with cooling models. Spectral classification also guides the search for brown dwarfs in surveys, since each class occupies characteristic regions in color magnitude diagrams. For example, L dwarfs appear red in near-infrared colors, T dwarfs appear bluer due to methane absorption, and wide dwarfs occupy even fainter and cooler regions of parameter space. The discovery of these classes also confirmed that the cooling of brown dwarfs proceeds in a continuous sequence rather than in abrupt jumps. Newly formed brown dwarfs may resemble late M stars, then pass into the L regime as silicate clouds, form then into the T regime as methane appears, and finally into the Y regime as ammonia dominates. Each stage is defined by temperature-dependent chemistry, not by internal nuclear processes. This continuity underscores the idea that brown dwarfs evolve smoothly over billions of years, providing a living record of substellar cooling. Important advances in classification came from large-scale infrared surveys. The 2-micron all-sky survey and the Sloan Digital Sky Survey discovered many of the first L and T dwarfs in the late 1990s and early 2000s. The Wide Field Infrared Survey Explorer added the first wide dwarfs in the early 2010s. These surveys established that brown dwarfs are common in the galaxy, scattered both in clusters and in the field. Follow-up with space telescopes such as Hubble and Spitzer provided more detailed spectra, while the James Webb Space Telescope is now extending measurements into the mid-infrared with unprecedented sensitivity. Each new instrument refines the classification by revealing subtler features in the spectra of faint objects. The classification also highlights the overlap between brown dwarfs and giant exoplanets. Directly imaged exoplanets with masses similar to brown dwarfs often show L or T-type spectra with methane absorption and silicate clouds. This similarity demonstrates that the same physics governs both free-floating brown dwarfs and planets bound to stars. Studying brown dwarfs therefore provides insight into the atmospheres of exoplanets, particularly in the challenging regime of low temperatures and complex chemistry. One ongoing challenge is to refine the boundaries between classes. The transition between L and T dwarfs, for example, occurs over a narrow temperature range yet involves large changes in appearance. This has led to debate about whether additional parameters such as surface gravity or metallicity influence the classification. Similarly, the distinction between the coldest T dwarfs and the warmest Y dwarfs is still being explored as the spectra are faint and overlap in features. The classification system is therefore still evolving as new data are gathered. Despite these uncertainties, the LT and Y sequence remains the cornerstone of brown dwarf research. It provides a clear structure for organizing the diversity of observed objects and connects directly to theoretical models of cooling and atmospheric change. Each class represents not a separate type of object, but a stage in the continuous evolution of a brown dwarf as it loses heat to space. This progression illustrates how fundamental physical processes, cooling, condensation, and molecular chemistry shape the observable universe at the smallest stellar scales. In summary, spectral classification of brown dwarfs into LT and Y provides a roadmap through their evolution. L dwarfs are dusty and red with silicate and iron clouds. T dwarfs are methane-rich with clearer skies, and Y dwarfs are extremely cool with ammonia and exotic condensates. These classes capture the essential stages of atmospheric transformation, as brown dwarfs cool, fade, and move step by step toward invisibility. The sequence is not only a tool for astronomers, but also a direct reflection of the physics of matter under conditions found nowhere else in the cosmos. Brown dwarfs are not static objects. They rotate, display variability in their light curves, and in some cases show signs of magnetic activity strong enough to generate radio emissions. These features distinguish them from the simple picture of fading embers and demonstrate that they remain dynamic even without hydrogen fusion. Understanding their rotation variability and magnetism helps astronomers probe their interiors and atmospheres, revealing processes that cannot be studied directly in most other astrophysical settings. Rotation is one of the most fundamental properties of brown dwarfs. Observations show that they rotate quickly compared to many stars. Periods of rotation often range from a few hours to a day, much faster than the Sun, which rotates about once every 25 days at its equator. The rapid rotation arises naturally from their formation. As a collapsing gas cloud contracts, conservation of angular momentum causes the object to spin more rapidly. With no strong stellar wind to carry away angular momentum as occurs in stars with fusion-driven outflows, brown dwarfs retain much of their spin. The result is a population of substellar objects that whirl rapidly throughout their lifetimes. The rotation of brown dwarfs can be measured by tracking periodic changes in brightness. If the atmosphere is uniform, the light curve remains steady. But in practice, most brown dwarfs display variations caused by patchy clouds or weather systems. As the brown dwarf rotates, different regions come into view, producing fluctuations in observed brightness. These variations provide indirect evidence of atmospheric dynamics. Monitoring over time reveals changes in amplitude and phase, suggesting that cloud patterns evolve, shift, and dissipate much like weather systems on giant planets. The timescales of variability range from hours corresponding to the rotation itself to days and weeks, indicating evolving atmospheric structures. Spectroscopic observations during rotation, known as Doppler imaging, provide further insight. By measuring subtle changes in spectral lines as different parts of the surface rotate into view, astronomers can reconstruct maps of cloud distribution. These reconstructions show that brown dwarfs can host large-scale features, possibly analogous to band spots or storms. Such results support the idea that their atmospheres are active, driven by convection, rapid rotation, and complex chemistry. In addition to rotation and variability, brown dwarfs display magnetic phenomena. Despite lacking hydrogen fusion, they generate magnetic fields through a dynamo process. Their interiors are fully convective, meaning that hot material circulates throughout the entire object rather than being confined to a zone. Combined with rapid rotation, this convection can amplify magnetic fields. Evidence for magnetism comes from radio observations. Some brown dwarfs emit periodic radio pulses reminiscent of those seen in magnetized planets such as Jupiter. These emissions are believed to be produced by the electron-cyclotron maser instability, a process in which electrons spiral along magnetic field lines and release coherent radio waves. The presence of such emissions confirms that brown dwarfs host strong organized magnetic fields. Magnetic fields also give rise to aurora-like phenomena. Just as charged particles interacting with Jupiter's magnetic field produce bright auroras near its poles, similar processes may occur on brown dwarfs. The detection of optical and infrared emissions linked to magnetic activity supports this interpretation. The fact that auroras can exist on objects without stellar-level fusion shows that magnetic phenomena are not confined to stars but extend to the broader population of substellar objects. The interaction between magnetism and rotation is complex. In stars, magnetic braking slows rotation over time as winds carry angular momentum away along magnetic field lines. In brown dwarfs, the absence of strong winds means that rotation does not slow as much. Nevertheless, some braking does occur, and older brown dwarfs may rotate more slowly than young ones. Measuring this trend provides clues about the efficiency of magnetic braking at substellar masses. Results so far indicate that brown dwarfs spin down more weakly than stars retaining rapid rotation for billions of years. Variability studies also reveal differences between spectral types. L dwarfs with thick silicate and iron clouds often show strong variability due to patchy clouds. T dwarfs where many clouds have settled can show even stronger changes as the last fragments of cloud cover break apart and expose clearer regions. Y dwarfs, though faint, may also display variability, but their signals are difficult to measure. Each spectral type provides a different window into how atmospheric dynamics evolve with cooling. The study of variability has practical implications as well. By monitoring brown dwarfs over long periods, astronomers can test models of cloud formation chemistry and mixing. The presence of evolving light curves shows that these objects are not simply passive spheres but bodies with dynamic evolving weather. In some cases, periodicity and variability can even be used to estimate wind speeds and circulation patterns. The analogy with giant planets is strong, yet brown dwarfs are hotter and more massive, offering a different regime for testing theories of atmospheric circulation. Radio detections of brown dwarfs also connect them to the broader field of planetary magnetism. The emissions are sometimes strong enough to rival those of stars, even though the total energy budgets of brown dwarfs are far lower. This efficiency suggests that magnetospheric processes in substellar objects can be highly effective at producing radio waves. Future instruments sensitive to low-frequency radio emissions may reveal many more examples, allowing detailed studies of magnetic cycles, auroral dynamics, and the relationship between magnetism and rotation. One of the ongoing questions is how magnetic activity changes as brown dwarfs cool. In stars, magnetic activity declines with temperature because cooler stars have less ionized material to sustain a dynamo. In brown dwarfs, as temperatures fall below 2000 degrees, the ionization level drops significantly. Yet magnetic fields are still detected, suggesting that even low levels of ionization are sufficient when combined with rapid rotation and convection. Understanding this persistence requires more detailed modelling of substellar dynamos and their interactions with partially ionized atmospheres. In summary, rotation variability and magnetism demonstrate that brown dwarfs are not inert relics, but active objects with dynamic interiors and atmospheres. Their rapid spins, patchy clouds, and magnetic fields produce observable signatures across the electromagnetic spectrum, from infrared light curves to radio pulses. These features provide rare opportunities to study weather circulation and magnetism in conditions that bridge the gap between stars and planets. The combination of quantum-supported interiors and restless surfaces makes brown dwarfs uniquely complex, ensuring that they remain central to the study of substellar astrophysics. Young brown dwarfs often reveal themselves through evidence of disks and signs of accretion. This connection to disks is significant because it reinforces the idea that brown dwarfs form in ways closely related to stars. In the earlier stages of star formation, collapsing clouds of gas and dust naturally develop rotating disks around the forming central object. These disks provide the material for both further growth of the central body and the potential formation of planets. Brown dwarfs, despite their low masses, are frequently observed to possess such disks during their youth, and in some cases they display clear signatures of ongoing accretion. These observations provide insight into their origins and early evolution. Infrared surveys have been essential for detecting disks around brown dwarfs. Warm dust in a disk emits strongly at infrared wavelengths, producing an excess of radiation beyond what the brown dwarf itself would emit. Instruments such as the Spitzer Space Telescope and the Atacama Large Millimeter Array have revealed infrared excesses in many young brown dwarfs, indicating that disks are common at early ages. The fraction of brown dwarfs with disks in star-forming regions is comparable to the fraction of stars with disks, suggesting that disk formation is a natural outcome of collapse, even at very low masses. Spectroscopic observations provide additional evidence. Some brown dwarfs show emission lines such as hydrogen alpha, which are typical signatures of accretion in young stellar objects. These lines arise when gas from the inner disk falls along magnetic field lines onto the central object, releasing energy as it impacts the surface. The presence of such accretion indicators confirms that brown dwarfs can undergo processes parallel to those in young stars. In some cases, the accretion rates measured are scaled-down versions of stellar rates consistent with their lower masses. Disks around brown dwarfs are not only markers of their youth, but also potential sites for planet formation. Observations with millimeter wavelength telescopes reveal that some disks contain substantial amounts of dust grains. Evidence of grain growth where tiny particles stick together to form larger aggregates has been detected. This process is the first step toward building planetesimals, the building blocks of planets. While it is unlikely that large planetary systems form around most brown dwarfs due to limited disk mass, smaller planets may still arise. This possibility blurs the line between stars' brown dwarfs and planets even further, since a brown dwarf with its own planetary system resembles a miniature star in function. Accretion and disk evolution also provide timing constraints. In star-forming regions a few million years old, many brown dwarfs still show signs of disks and accretion. In older clusters, the fraction declines, suggesting that disks around brown dwarfs dissipate on timescales, similar to those around stars, typically a few to 10 million years. This pattern indicates that the physical processes of disk clearing, such as photoevaporation winds and accretion, operate across the mass spectrum. The presence of disks in the youngest brown dwarfs therefore provides a window into their formative period before they settle into long-term cooling. Disks can also influence the rotation of young brown dwarfs. When a disk is present, magnetic interactions between the disk and the brown dwarf can regulate spin, a process sometimes called disk locking. Once the disk dissipates, the brown dwarf is free to spin up as it contracts. This interplay may explain why young brown dwarfs show a range of rotation rates, with some spinning relatively slowly compared to older counterparts. The role of disks in regulating early rotation is an area of ongoing study connecting the physics of magnetism, accretion, and angular momentum. Another dimension of disk studies is multiplicity. Some brown dwarfs are found in binary systems where both members have disks while others orbit stars as wide companions with their own disks intact. These configurations suggest that disk survival is common in a variety of environments, not limited to isolated brown dwarfs. The diversity of disk-bearing systems points to the robustness of disk formation across a wide range of initial conditions. In addition to dust disks also contain gas, though measuring gas is more difficult than dust. Observations of molecular lines such as carbon monoxide provide evidence that gas-rich disks exist around young brown dwarfs. The gas component is critical for accretion and for the potential formation of gas giant planets. However, the total gas masses in brown dwarf disks are typically smaller than in stellar disks, making the likelihood of forming large gas giants low. More common may be smaller rocky or icy bodies analogous to terrestrial planets or dwarf planets in the solar system. The study of disks around brown dwarfs also informs the question of how they form. If brown dwarfs originated primarily through ejection from forming clusters, as one scenario suggests, then their disks might be truncated or absent because ejection would strip away much of the surrounding material. The fact that many young brown dwarfs retain substantial disks suggests that ejection is not the only pathway. Direct collapse and disk fragmentation likely account for many cases allowing disks to remain intact. The presence of disks therefore serves as evidence against ejection being the dominant formation channel, although it may still occur in some environments. As brown dwarfs age, their disks dissipate and accretion stops. The absence of infrared excess in older brown dwarfs shows that the disks vanish within a few tens of millions of years, similar to stars. Once the disk is gone, the brown dwarf enters its long phase of cooling and fading. By then, any planets that might have formed around it are left to orbit a faint central body. Detecting such planets remains challenging due to the faintness of brown dwarfs and the small sizes of their planetary systems, but future instruments may reveal whether they are common. In summary, disks and accretion in young brown dwarfs demonstrate that their early lives parallel those of stars. They form disks of gas and dust accrete material onto their surfaces and show signatures of active magnetospheric processes. These disks may produce small planets, although limited masses restrict their scale. The presence of disks also helps distinguish formation pathways and provides constraints on timescales for early evolution. Studying brown dwarf disks not only clarifies their own nature, but also sheds light on the universality of disk physics across the full range of astrophysical objects, from massive stars down to the smallest substellar bodies. The companions of brown dwarfs and the question of where to draw the boundary between brown dwarfs and planets provide another dimension to their study. Brown dwarfs are often found in binary or multiple systems, sometimes paired with stars, sometimes paired with other brown dwarfs, and sometimes existing as companions to massive planets. These configurations reveal both how brown dwarfs form and how they fit into the broader classification of astronomical objects. Binary systems containing two brown dwarfs are of particular importance. When two brown dwarfs orbit each other, astronomers can measure their orbital motions and apply the laws of gravity to determine their masses directly. These measurements provide benchmarks for testing theoretical models of brown dwarf evolution. Without such dynamical mass measurements, estimates of mass rely on uncertain assumptions about age and cooling. Binary systems therefore serve as critical laboratories, providing data that anchor the classification of brown dwarfs. Observations show that binary brown dwarfs tend to have small separations, often less than 20 astronomical units, and mass ratios close to unity. These trends suggest that binary brown dwarfs form together from the same fragment of a molecular cloud rather than by capture. Brown dwarfs are also found as companions to stars. Some orbit closely, while others are located at hundreds or even thousands of astronomical units from their primaries. Interestingly, there is a relative scarcity of brown dwarf companions at intermediate distances of a few astronomical units, a phenomenon sometimes called the brown dwarf desert. Surveys for exoplanets around Sun-like stars find many giant planets at such distances, and many stellar companions but relatively few brown dwarfs. This desert may reflect formation processes, with brown dwarfs less likely to form in disks like planets, and less likely to remain bound at moderate separations compared to stars. At wider separations, however, brown dwarfs are more common, consistent with formation through fragmentation of the molecular cloud rather than disk processes. Some brown dwarfs themselves have planetary companions. Direct imaging surveys have detected small planets orbiting brown dwarfs, though these systems are rare and difficult to observe. The fact that such planets exist shows that even faint substellar objects can host miniature planetary systems. This finding blurs the boundaries between brown dwarfs and stars, since the functional role of hosting planets is shared. It also raises questions about how such systems form, given the limited mass of brown dwarf disks. Small rocky planets or icy bodies may be the most common outcomes, though gas giant companions have also been found in some cases. The boundary between brown dwarfs and planets remains debated. The deuterium burning threshold at about 13 Jupiter masses provides a convenient physical dividing line. Objects above this mass can briefly fuse deuterium, while those below cannot. However, this criterion does not capture differences in formation. Some objects above 13 Jupiter masses may form in planetary disks rather than through cloud collapse, making them planets in terms of origin. Conversely, some objects below 13 Jupiter masses may form directly from collapsing clouds, making them more like very low-mass brown dwarfs. Because formation is often difficult to determine, observationally classification is sometimes ambiguous. Astronomers therefore use both mass and formation context when possible, acknowledging that no single definition covers all cases. Multiplicity studies also reveal how common brown dwarfs are as companions compared to stars and planets. Surveys show that brown dwarf binaries are less frequent than stellar binaries, with estimates of about 15% of brown dwarfs found in binaries, compared to a much higher fraction for stars. This lower multiplicity suggests differences in formation or survival. The tendency for brown dwarf binaries to have nearly equal masses may reflect fragmentation processes that favor symmetric splitting at small scales. The rarity of brown dwarf companions at intermediate separations from stars also constrains models of disk instability and migration. The presence of brown dwarfs in hierarchical systems adds further complexity. Some stars host both stellar companions and brown dwarf companions, forming triples or higher-order systems. These arrangements illustrate the wide range of possible outcomes in star-forming regions. Brown dwarfs can be central objects with their own planets, secondary companions to stars, or paired with each other. This diversity underscores that brown dwarfs are integral members of the population of astrophysical bodies rather than outliers. Companionship studies also highlight the role of environment. In dense clusters, dynamical interactions can disrupt wide brown dwarf pairs, leaving only close binaries. In looser environments, wide pairs can survive. Observations confirm that wide brown dwarf binaries are more common in sparse regions. This environmental dependence supports the idea that brown dwarfs form in similar ways to stars but are more fragile to disruption. The distinction between brown dwarfs and giant exoplanets is further blurred by direct imaging. Many of the directly imaged exoplanets discovered around young stars have masses near or above the deuterium burning threshold, overlapping with the brown dwarf regime. Their spectra often resemble L or T dwarfs with silicate clouds and methane absorption. In practice, these objects are often called planets because they orbit stars and likely formed in disks. The similarity in properties, however, shows that mass alone cannot be the full story. Brown dwarfs and giant planets form a continuum with boundaries defined as much by context as by physics. Understanding companions also informs the broader galactic census. If brown dwarfs are often found as companions, their numbers may be underestimated when surveys focus on isolated objects. Conversely, the rarity of brown dwarf companions in certain ranges indicates that their population is not evenly distributed across all environments. These patterns provide constraints on formation theories, such as whether fragmentation or disk processes dominate under different conditions. In summary, companions and boundaries reveal both the diversity and the ambiguity of brown dwarfs. They form binaries with each other, orbit stars at a wide range of distances, and sometimes host their own planets. The boundaries between brown dwarfs and planets are defined partly by deuterium, burning partly by formation and partly by context. While the classification remains flexible, the study of companions provides essential data for testing models of mass cooling and evolution. Brown dwarfs are therefore not solitary oddities but active participants in the network of multiple systems that populate the galaxy, bridging the divide between stars and planets in both physical properties and companionship. To understand the role of brown dwarfs in the galaxy, astronomers study their population statistics and distribution. These studies ask how common brown dwarfs are, how their numbers compare with stars and planets, and what their presence reveals about the process of star formation. By surveying large areas of the sky and compiling catalogues of brown dwarfs, researchers can build the initial mass function at the low mass end. This function describes the number of objects formed at each mass, and is a key measure of how matter organizes itself in molecular clouds. The initial mass function for stars rises toward lower masses, meaning that low-mass stars are more common than massive ones. The question has long been whether this trend continues into the brown dwarf regime or whether it declines. Early predictions suggested that brown dwarfs might be rare since their faintness made them difficult to detect. However, large infrared surveys in the late 20th and early 21st centuries reveal that they are widespread. The 2-micron all-sky survey and the Sloan Digital Sky Survey discovered many L and T dwarfs, while the Wide Field Infrared Survey Explorer extended detections into the Y class. These surveys confirmed that brown dwarfs exist in large numbers, though not as numerous as stars. When the counts are plotted as a function of mass, the number of objects increases down to about a few tenths of a solar mass, then flattens and begins to decline in the brown dwarf range. This flattening indicates that while brown dwarfs are common, they are less common than low-mass stars. The decline continues into the planetary mass regime below the deuterium burning limit. This shape of the distribution supports the view that star formation is less efficient at very low masses, perhaps because fragments of molecular clouds below a certain threshold are easily disrupted or cannot collapse fully. The fraction of brown dwarfs compared to stars varies depending on environment. In dense clusters such as the Orion Nebula surveys have identified many brown dwarfs mixed among stars with ratios of roughly 1 brown dwarf for every 4 to 6 stars. In looser associations, the ratio can be different. The overall galactic average suggests that brown dwarfs make up a significant fraction of the population, though they contribute much less total mass than stars. Because they are low mass and faint, their cumulative contribution to galactic light and mass is small compared to stars, but their numbers still influence the dynamics and demographics of stellar populations. Spatial distribution provides additional insights. Brown dwarfs are found both in clusters and in the field, meaning they are present not only near their birthplaces, but also dispersed throughout the galaxy. Many are discovered as isolated objects drifting alone. Others are found in wide pairs or associations with stars. Their widespread distribution confirms that they are a natural outcome of star formation across many environments. However, the details vary. In some young clusters, brown dwarfs appear more centrally concentrated, while in others they are spread more evenly. These differences may reflect local dynamics such as ejection of low-mass objects from crowded regions. Population studies also provide information about the ages of brown dwarfs. Because they cool steadily over time, brightness is linked to age as well as mass. To disentangle these factors, astronomers study brown dwarfs in clusters with known ages. For example, in the Pleiades cluster, which is about 100 million years old, brown dwarfs appear brighter than field brown dwarfs of similar mass consistent with their youth. In older clusters, they appear fainter. These comparisons calibrate cooling models and allow researchers to estimate ages of field brown dwarfs. By assembling large samples, astronomers can trace the age distribution and infer-star formation histories in the galaxy. The contribution of brown dwarfs to the overall mass of the Milky Way has also been studied. At one time, brown dwarfs were considered candidates for the unseen mass known as dark matter. If they were extremely abundant, they could account for a significant fraction of the galaxy's missing mass. Surveys, however, have shown that while numerous brown dwarfs are not abundant enough to explain dark matter, their total mass contribution is less than a few % of the galactic disk. This result clarified that dark matter must be of non-luminous and non-baryonic origin, rather than simply an unseen population of faint substellar objects. Population statistics further highlight the connection between brown dwarfs and exoplanets. Many directly imaged exoplanets have masses overlapping with brown dwarfs, and their spectra resemble L or T dwarfs. The distribution of masses in both populations suggests continuity rather than a strict separation. Still, differences in frequency and location hint at distinct formation channels. Planets are common at small orbital separations from stars, while brown dwarfs are rare in that regime, but more common as free-floating or wide companions. This pattern supports the idea that planets form in disks and brown dwarfs form more like stars. The future of population studies will rely on even more sensitive instruments. The James Webb Space Telescope can detect extremely faint white dwarfs, extending the census to the coldest and oldest brown dwarfs. The Gaia mission, though primarily an optical survey, provides parallaxes for brighter brown dwarfs, giving accurate distances and allowing precise luminosity measurements. Ground-based observatories with adaptive optics also contribute by resolving binaries and measuring dynamical masses. Together, these efforts build a more complete picture of the low-mass population. Understanding the statistics of brown dwarfs is not only about counting them, it also constrains theories of star formation, informs models of galactic structure, and provides context for the diversity of planetary systems. By mapping the distribution of masses from stars down through brown dwarfs into planets, astronomers can test whether a single unified process explains all outcomes or whether different mechanisms dominate in different regimes. The evidence so far points to a continuum shaped by gravity, turbulence, and environment, with brown dwarfs filling the space between stars and planets, both literally and conceptually. In summary, population and distribution studies show that brown dwarfs are common but not dominant. They exist in large numbers across the galaxy, with ratios to stars that vary by environment. They contribute modestly to the galaxy's mass but significantly to our understanding of star formation. Their presence in clusters, associations, and the field demonstrates that they are integral members of the stellar population, not anomalies. The shape of the initial mass function at the low mass end, with its flattening and decline, reflects the limits of nature's ability to assemble objects from molecular clouds. Brown dwarfs therefore stand as statistical witnesses to the physics of star formation, silent markers of the processes that govern the distribution of mass in the universe. At the coldest end of the brown dwarf sequence lie the Y dwarfs, which represent the extreme limits of current observational capabilities. These objects are so cool and faint that they challenge the boundaries of what can be detected even with advanced infrared telescopes. Their discovery and study reveal how far the cooling of brown dwarfs can progress within the current age of the universe, and provide a glimpse into a class of objects that bridge the gap between the warmest planets and the faintest substellar bodies. Dwarves are defined by surface temperatures below about 500 degrees. Some estimates for the coolest examples place their temperatures near 250 degrees, not much warmer than a summer day on Earth. At these temperatures, the chemistry of the atmosphere changes dramatically compared to hotter brown dwarfs. Molecules such as ammonia, which cannot survive in warmer atmospheres, become prominent absorbers. Water vapor remains important, and additional condensates, such as sulfides and water ice, may form clouds. These changes give I dwarf spectra unique shapes, distinct from the L and T dwarfs that precede them. The faintness of I dwarfs means they are almost invisible in optical light. Their peak emission lies in the mid-infrared, where the human eye cannot see. Instruments designed for infrared astronomy are required to find them. The Wide-Field Infrared Survey Explorer played a key role in their discovery by mapping the entire sky at multiple infrared wavelengths. Its sensitivity allowed the detection of very faint, cool objects that had gone unnoticed in earlier surveys. Follow-up with the Spitzer Space Telescope confirmed their nature, and more recently the James Webb Space Telescope has provided higher resolution spectra that reveal details of their atmospheric chemistry. Observations show that Y dwarfs can have luminosities thousands of times lower than the faintest stars. They emit only a tiny fraction of the sun's energy, making them among the dimmest natural objects ever observed beyond the solar system. Despite this faintness, they still glow faintly with the residual heat of formation. The fact that we can detect them at all demonstrates the sensitivity of modern instruments and the importance of space-based infrared astronomy. The discovery of Y dwarfs has expanded the known diversity of substellar objects. Before their identification, the coolest known brown dwarfs were T dwarfs, with temperatures of about 700 degrees. E dwarfs extend this range by hundreds of degrees downward, proving that cooling proceeds to much lower limits than previously documented. This extension confirms theoretical models predicting that old brown dwarfs, billions of years after formation, should become as cool as giant planets. The coldest Y dwarfs we see today are likely ancient objects perhaps as old as the galaxy itself. Studying Y dwarfs provides tests of atmospheric models in regimes not accessible elsewhere. The appearance of ammonia features the behavior of water clouds, and the impact of very low temperatures on molecular abundances are all areas of active research. These studies are difficult because spectra of Y dwarfs are faint and noisy, requiring long exposures with sensitive instruments. Even so, the data obtained so far confirm that the chemical processes predicted for cool atmospheres do occur, lending confidence to models that are also applied to exoplanets. Dwarfs therefore serve as analogues for gas giant exoplanets, allowing researchers to study planetary-like conditions without the interference of a bright host star. The challenge of distinguishing dwarfs from planets highlights the blurred boundary between categories. Free-floating wide dwarf with a mass of 10 Jupiter masses may look spectroscopically identical to a giant exoplanet of similar mass orbiting a star. The only difference is context. This overlap emphasizes again that nature produces a continuum of outcomes from stars through brown dwarfs to planets. The Y-class, by reaching into the planetary temperature range, makes this continuum especially evident. The distribution of white dwarfs across the galaxy is still being mapped. Because they are so faint, only nearby examples have been detected. Some are among the closest systems to the Sun within a few parsecs. Their proximity is not surprising since faint objects can only be detected nearby, but it also highlights that the solar neighborhood likely contains many such cold bodies awaiting discovery. Estimates suggest that the number of white dwarfs may be comparable to, or even exceed the number of stars in the immediate vicinity, though their contribution to mass is small. The study of white dwarfs also connects to the question of how brown dwarfs evolve over cosmic time. The oldest brown dwarfs, formed more than 10 billion years ago, have had sufficient time to cool into the Y regime. The fact that we detect white dwarfs today demonstrates that cooling proceeds as predicted by theory. However, uncertainties remain about details such as cloud physics, atmospheric mixing, and metallicity effects. Observations of white dwarfs provide crucial data to refine these aspects of the models. The James Webb Space Telescope has already provided breakthroughs by capturing detailed spectra of white dwarfs across a wide wavelength range. These observations reveal ammonia bands, water absorption, and evidence of new cloud species. They also show variability in some cases, suggesting that even at low temperatures weather systems exist. These results confirm that white dwarfs are not static but dynamic, with atmospheres shaped by processes similar in principle to those on warmer brown dwarfs and giant planets. Detecting colder objects beyond the Y-class may be possible with future instruments. Theoretical models predict that if the universe were old enough, brown dwarfs would eventually cool below 200 degrees, approaching the temperature of the cosmic microwave background. Such objects would be nearly impossible to detect with current technology. For now, the Y-class marks the observational limit, representing the faintest glow of brown dwarfs in their final observable stages. In summary, white dwarfs extend the known sequence of substellar objects to the coldest temperatures yet observed. They are faint infrared luminous bodies with unique chemistry dominated by ammonia water and exotic clouds. Their discovery required sensitive space-based surveys, and their study continues to refine our understanding of atmospheric physics at the lowest temperatures. They demonstrate the long-term cooling trajectory of brown dwarfs and blur the boundary with giant planets, emphasizing the continuity of nature's outcomes. Though faint and difficult to study, white dwarfs are essential for completing the picture of brown dwarf evolution and for testing theories of matter and chemistry under extreme conditions. Although astronomers have made great progress in understanding brown dwarfs, many questions remain unresolved. These uncertainties arise because brown dwarfs occupy a complex region of parameter space where stellar and planetary physics overlap. Their faintness makes them difficult to observe, and their atmospheres and interiors involve processes that are challenging to model accurately. The open debates span topics such as formation channels, cloud models, metallicity effects, and weather dynamics, and each represents an active area of research. One of the most important open questions concerns the precise formation mechanisms of brown dwarfs. As described earlier, three major pathways are proposed: direct collapse of a small fragment of a molecular cloud fragmentation of circumstellar disks and ejection of low-mass protostars before they can grow to stellar size. Evidence exists for each scenario, yet the relative contributions remain uncertain. In some regions, the ratio of brown dwarfs to stars appears higher, which might suggest that certain environments favor their production. In other regions, the ratio is lower. Determining whether one pathway dominates or whether all occur with significant frequency remains a goal of both simulations and surveys. Advances in computational models of cloud fragmentation and disk instability are helping clarify the likelihood of each scenario, but observations are still needed to anchor these results. Cloud formation and behavior in brown dwarf atmospheres present another set of unresolved problems. Clouds of silicates, iron, and more exotic compounds strongly influence the spectra and colors of brown dwarfs, yet modeling them accurately is extremely difficult. Cloud particle size distributions, vertical mixing and condensation processes are complex and depend on temperature, pressure, and chemical composition. Observations show large variability in brightness among brown dwarfs, indicating patchy and evolving cloud coverage. However, current models often assume uniform cloud layers, which fail to capture the observed dynamics. The transition from L to T spectral types, where clouds dissipate or sink below the photosphere, remains especially puzzling. Astronomers debate whether this transition is driven mainly by cloud breakup chemical changes or variations in surface gravity. Detailed variability monitoring and high-resolution spectra are helping address these questions, but no consensus has yet emerged. Metallicity, which refers to the abundance of elements heavier than hydrogen and helium, also plays a key role but is difficult to measure in brown dwarfs. Metallicity affects molecular abundances, cloud formation, and cooling rates. For stars, metallicity is determined through well-established spectroscopic techniques, but brown dwarf spectra are dominated by broad molecular bands rather than sharp atomic lines, making metallicity harder to constrain. Some studies suggest that low metallicity brown dwarfs have distinct spectral characteristics, while others argue that surface gravity and cloud effects complicate the interpretation. Resolving the influence of metallicity is crucial for applying brown dwarf models to exoplanets, since planets around stars of different metallicities may show similar atmospheric behaviors. Weather dynamics represent another frontier. Brown dwarfs rotate rapidly and have fully convective interiors, creating conditions for strong atmospheric circulation. Observations of periodic variability confirm the presence of large-scale weather systems, but the details of these systems remain unknown. Are the variations caused by long-lived storm systems, bands similar to those on Jupiter, or rapidly evolving turbulent structures? Multi-wavelength monitoring shows that different layers of the atmosphere vary at different times, suggesting complex vertical structures. Understanding these dynamics requires three-dimensional models of atmospheric circulation that include rotation, convection, cloud formation, and radiative transfer. Such models are still being developed and tested against the limited observational data available. The physics of magnetic fields in brown dwarfs is another area with uncertainties. Radio emissions demonstrate that strong magnetic fields exist, yet the mechanism for sustaining them in such cool and partially neutral atmospheres is debated. Dynamos in stars rely on ionized plasma, but in brown dwarfs the degree of ionization is much lower. Some models suggest that even a small fraction of ionized gas is enough when combined with rapid rotation and convection. Others argue that different dynamo processes may be operating. The efficiency of magnetic braking, which slows rotation in stars, also appears reduced in brown dwarfs, but the reasons for this are not fully clear. Continued radio observations and theoretical work on dynamos in partially ionized fluids are needed to resolve these questions. Another unresolved issue is the precise boundary between brown dwarfs and giant planets. The deuterium burning threshold provides a physical guideline, but formation processes blur the distinction. Objects below 13 Jupiter masses can form through cloud collapse, while objects above this limit can form in disks. The classification therefore depends on both mass and origin, but origin is rarely observable directly. This ambiguity creates difficulties when assigning labels to newly discovered objects, especially in the overlapping mass range. Some astronomers argue for a definition based purely on mass, while others prefer one based on formation history. For now, both approaches are used depending on context. Cooling models of brown dwarfs, though generally successful, also contain uncertainties at the coldest temperatures. The Y dwarfs discovered so far confirm that cooling proceeds to very low levels, but discrepancies remain between predicted and observed brightnesses. Some Y dwarfs appear fainter or brighter than models predict for their estimated ages and masses. These mismatches suggest that cloud physics, chemical disequilibrium, or other processes are not fully captured in current models. Improved data from the James Webb Space Telescope are helping refine these models, but more work is needed to achieve consistency across the full range of temperatures. Population statistics raise further questions. While surveys have revealed many brown dwarfs, the true distribution at the lowest masses is still uncertain. Are planetary mass brown dwarfs below the deuterium burning threshold common as free-floating objects, or are they rare? Some micro-lensing surveys suggest that such objects may be abundant, while direct imaging surveys suggest fewer. Reconciling these results requires more sensitive searches and better models of detection biases. The frequency of brown dwarfs as companions to stars also remains a puzzle, especially the apparent scarcity at intermediate orbital distances known as the brown dwarf desert. Whether this desert reflects real formation physics or observational limitations continues to be investigated. The study of unresolved questions about brown dwarfs matters not only for their own sake, but also for broader astrophysics. Brown dwarfs are natural laboratories for testing physics under conditions intermediate between stars and planets. Improving models of their clouds and atmospheres helps interpret exoplanet spectra. Understanding their formation channels informs theories of star formation. Measuring their numbers and distribution constrains the initial mass function. Their magnetism provides insights into dynamos in low ionization environments. Each uncertainty represents both a challenge and an opportunity for discovery. In summary, the science of brown dwarfs is not finished but in motion. Open debates about formation pathways, cloud behavior, metallicity effects, weather dynamics, magnetism, classification, and cooling models ensure that the field remains active. As instruments improve and surveys expand, many of these uncertainties will be reduced, but some may reveal new layers of complexity. Brown dwarfs, faint though they are, continue to illuminate the frontier between stars and planets, raising questions that drive the refinement of astrophysical theory. The detection and characterization of brown dwarfs rely on specialized observational techniques, since they are faint and emit most of their radiation in the infrared. Over the past several decades, advances in infrared astronomy, precise astrometry, and spectroscopic analysis have made it possible to identify and study thousands of these objects. Each method contributes different pieces of information, from locating new brown dwarfs to measuring their distances, temperatures, compositions, and variability. Together, these techniques form a comprehensive toolkit for exploring the substellar population. Infrared surveys were the breakthrough that made brown dwarf astronomy possible. Because brown dwarfs cool steadily and emit primarily at long wavelengths, they are almost invisible in optical light. Early surveys, such as the 2-micron all-sky survey, scanned the sky at near-infrared wavelengths and discovered the first large populations of L and T dwarfs. The Sloan Digital Sky Survey, although primarily optical, also identified brown dwarfs through their unusual colours and faintness. Later, the Wide-Field Infrared Survey Explorer extended sensitivity to longer wavelengths, making it possible to detect the much colder white dwarfs. These wide surveys provide candidate lists which are then confirmed and studied in greater detail with follow-up observations. Once a candidate brown dwarf is found, parallax measurements provide its distance. Parallax is the apparent shift in an object's position on the sky as Earth orbits the Sun. By measuring this shift precisely, astronomers can calculate distance and therefore determine intrinsic brightness. The Gaia mission has provided parallaxes for many relatively bright brown dwarfs, while ground-based campaigns using dedicated telescopes continue to refine distances for fainter ones. Accurate distances are crucial for comparing observations with theoretical models, since brightness alone does not reveal whether an object is intrinsically faint or simply far away. Spectroscopy is the primary tool for characterization. By dispersing light into its component wavelengths, astronomers can identify absorption features caused by molecules and atoms in the atmosphere. For L dwarfs, spectra show metal hydrides, alkali metals and dusty clouds. For T dwarfs, methane absorption becomes prominent. For Y dwarfs, ammonia bands appear. The detailed shapes and depths of these features provide information about temperature, surface gravity, and atmospheric chemistry. High-resolution spectroscopy also allows the measurement of radial velocities, which reveal motion along the line of sight and contribute to kinematic studies of the brown dwarf population. Photometric monitoring adds another layer of information. By measuring brightness over time, astronomers detect variability caused by rotating cloud patterns and evolving weather systems. These light curves can be periodic, corresponding to rotation, or irregular, corresponding to dynamic atmospheric processes. Monitoring across multiple wavelengths reveals that different atmospheric layers vary differently, giving insight into vertical structure. Long-term monitoring helps identify trends such as magnetic activity cycles or evolving cloud systems. Radio observations have also become a surprising but important method. Some brown dwarfs emit strong radio pulses thought to be generated by aurora, like processes linked to magnetic fields. These emissions can be periodic, tied to rotation, and provide a unique probe of magnetism in substellar objects. Radio detections confirm that strong magnetic fields exist even in cool, low ionization atmospheres, and they open a new observational window for studying brown dwarfs alongside traditional infrared and optical techniques. In addition to individual detections, statistical surveys are essential for understanding the population as a whole. By combining wide-area surveys with follow-up characterization, astronomers build luminosity functions and mass distributions. These statistical measures reveal how many brown dwarfs exist in different mass ranges and environments. For example, counts in young clusters provide age-constrained samples, while field surveys build the overall census of nearby brown dwarfs. Together, these results inform the initial mass function and constrain theories of star formation. Binaries and multiples provide especially valuable data. When brown dwarfs are found in binary systems, their orbital motions allow direct determination of masses. Mass is the most fundamental property of any star or substellar object, but it is normally inferred indirectly. Dynamical measurements in binaries provide precise benchmarks that test cooling models and atmospheric theories. High-resolution imaging with adaptive optics and space telescopes has identified many such binaries, and long-term monitoring continues to refine their orbits and masses. Spectral energy distributions constructed by combining measurements across many wavelengths provide another tool. By assembling data from optical, infrared, and sometimes radio observations, astronomers can calculate total luminosities. These values, when combined with distances, allow comparison with models of brown dwarf cooling. Spectral energy distributions also reveal peculiarities such as excesses from disks in young brown dwarfs, or unusual absorption features that suggest non-equilibrium chemistry. The James Webb Space Telescope is now pushing the field further. Its sensitivity and resolution in the mid-infrared allow detailed spectra of white dwarfs that were previously too faint to study. Webb can detect ammonia absorption water features and even possible cloud signatures in objects only a few hundred degrees above absolute zero. These observations refine atmospheric models and test predictions of chemistry and cloud physics under conditions never accessible before. Webb also extends the search for even colder and fainter objects, potentially identifying the lowest mass free-floating bodies in the solar neighborhood. Other space missions contribute complementary data. The Spitzer Space Telescope operating before Webb provided crucial mid-infrared photometry of many brown dwarfs, building the foundation for the wide dwarf class. The Hubble Space Telescope contributed near-infrared spectra and imaging of faint companions. The Gaia mission, though limited in sensitivity to faint infrared objects, provides astrometric measurements for brighter brown dwarfs and helps tie their distances to the broader stellar population. Together, these facilities create a multi-wavelength, multi-technique approach that has transformed brown dwarf science. Looking forward, upcoming surveys such as those from the Vera C. Rubin Observatory will expand the census of faint variable objects, and radio arrays will search systematically for magnetic emissions. Combining these datasets will continue to refine the picture of brown dwarfs as a diverse population with varied atmospheric, magnetic, and evolutionary properties. In summary, the detection and characterization of brown dwarfs rest on a combination of wide infrared surveys, precise distance measurements, detailed spectroscopy, variability monitoring, and increasingly radio astronomy. Each technique adds a layer of understanding, from discovery to classification to physical properties. The synergy of these methods has turned brown dwarfs from theoretical predictions into well-studied members of the galactic population. They remain faint, elusive, and challenging to observe, yet with modern instruments their secrets continue to emerge, filling in the picture of the universe between stars and planets.